So basically, as we have seen, in case of metamaterial, we should be having a dynamic loading, right? Once we have dynamic loading, then structure will be having its response in terms of wave, right? So as usual in mechanical engineering or civil engineering or in aerospace, we want that we may be having external load or external source, but the structure should not have any vibrations or any noise, right? So question actually is how we will control this or how we will overcome this. So the idea actually is if we can control the waves, that is, if we can diminish the waves, then there will not be any vibrations, right? So we have seen actually, that is, we have two types of vibrations, or say we have two types of waves. One wave actually has higher wavelength, other one has lower wavelength. Or in terms of, we can say, frequency, we have higher frequency wave, that is lower wavelength wave, and we have lower frequency wave, that is higher wavelength, right, reverse. So we want to control the vibrations of low frequency, then we have to remove the higher wavelength waves, right? So basically the higher frequency wavelength wave actually can be diminished with the periodicity. That is, if you have a periodic structure, that is, if the matter atoms are arranged in the periodic fashion, then actually they can be diminished. I mean, waves can be diminished. So we have to prove this. The second part, that is, to diminish the higher wavelength waves or to control the low frequency vibrations. For that, we need to have a resonator, a local resonator. And actually, that local resonator is nothing but is here piezoelectric material or piezoelectric metamaterial, right? A piezoelectric meta atom, right? So we have the structure and we have the piezoelectric meta atom. So we have piezoelectric meta atoms in the periodic fashion, then they can diminish the higher frequency waves or higher frequency vibrations. And since the piezoelectric metal actually respond, the piezoelectric materials actually behaves as the bridge between mechanical domain and electrical domain, then they can also be used to diminish the low frequency response. So then let us discuss first how to diminish or how to overcome the low frequency response or lower frequency vibrations or low frequency wavelength, right? So what I have say again to make our discussion very simple, let we have say one dimensional structure. It may be a rod, right? And further you may actually can consider rod in terms of mass and springs. So, we can assume that we will be having infinite number of rods, we have infinite number of springs, and we have infinite number of masses, right. So, say what we have so say what we have say this mass, we have say this spring, we have say this mass, we have say this spring, we have this mass, we have this spring, right. Actually system is very long, considering we have infinite number of spring and masses, right. Let's suppose this is my nth number of spring, and again we are assuming that every spring has same stiffness, right, and say every spring has say same mass, yes. Let us say this spring, this mass actually is my mass of nth number of spring, it's a mass, so say Mn, right, and say this is, we have say Kn, right, and as such this will be having displacement. So, say is Un, say this actually is my spring n minus 1, right, this is say Un minus 1. Similarly, we will be having displacement, this is Un plus 1. So, I want to see actually, since all the springs and all the mass are the same, so actually if we understand the dynamics of one set mass and spring, then I can understand of complete spring and mass, and hence the wave, right. So, let us, we want to see actually the dynamics of nth mass and spring. So, we can make the FVD of this. So, since this moving with the displacement of Un, this also Un plus 1. So, on this mass there will be force applied by this spring, so called spring of n plus 1 and spring n minus 1, right. The force applied on this mass will be having from these springs n plus 1 and n plus 1, and so this is my say n minus 1, right. So, can you see the force applied by say left spring? So, we have force applied by left spring means F n minus 1 is equal to minus K, of course K n minus 1. Since all the springs actually have the same same stiffness, so K1, K2, Kn minus 1, Kn, Kn plus 1 and dot dot dot, they all have the K. So, the force applied by the spring n minus 1 on the spring, this mass n, will be having what? Minus K and un minus un minus 1. Similarly, force applied by n plus 1 spring is equal to minus k un plus minus un plus 1, right. Now, इरेजर कहाँ है?
सर यही वाला है सर, ऑल द ऑप्शंस एंड कलर आल्सो हियर सर.
Yes. Now see, we want to have a local resonator, so-called piezoelectric material, piezoelectric patch. Suppose we have the piezoelectric patch, say here. And this will be having a stiffness, so-called say Kr resonator, and it will be having a mass, say Mr, right? And say the displacement of this is, that is displacement of resonator, say is B n. So we have mass Mr and Kr, stiffness of the resonator, and the velocity we have Vn. Really, I'm sorry. This is Br. So, of course, the piezoelectric metal will apply a force because of this of electric circuit. Let's suppose at the moment we are not considering this force, we are considering this as the mass element, that is it has the mass Mr and Kr actually is the stiffness. So, force applied by piezoelectric material on the mass Mr, Mn is what? That is minus K and Un minus Vn. Yes. So the resultant force M F is equal to this actually this is on the piezoelectric, so on the this main mass, that is mass of the rod, right, Mn. So we can keep all the forces here, and then the equation will be so called M n Un dot plus K Un minus 1 minus plus K Un minus Un plus 1 and plus K Un minus, this is Kr, right? This is Kr. So actually this is the equation for the main mass, right? Similarly, we can have the equation for so-called the free body diagram of this resonator, and that will be what? Will be MR and say BR so BR double dot plus K, and in this case it will be Bn minus Un is equal to 0. So we have these two equations, right? Yes. So actually at the moment I am considering this as simple resonator. I am not using here piezoelectric concept. So basically this is a mechanical resonator, right? It may be anything. Now I want to see the response for this. Basically I want to see, right, that is the frequency response or how the baby is traveling in this system. So for that I may assume a solution for this, right? So let us assume solution. So basically solution for Un is equal to say U naught, and that is E raised to power I omega t, right? Similarly, we can assume solution for Bn is equal to B naught E I omega t. In fact, I should use minus sign. Yes. Now, actually, this solution is for the individual masses, right? For example, if I want to know the response of this mass Mn and response of Mr, I can have. But actually, this I want to have a general equation that will apply for all, right? So there was a scientist so-called Baloch. He proposed, he modified this equation, that in case of periodic structure, but we can have this U naught actually is given by capital U, which is a function of wave number k, capital K. Actually, small k is my stiffness, capital K is the wave number. And this wave number actually is a function of omega. Omega is the frequency. U is a function of capital K. Capital K is my wave number, right? It's a function of omega, right? And E raised to power. So basically what we have this as my origin, x. So let us, the distance between two corresponding masses is d, right? And suppose I have up to here n number of masses. So this distance actually is my, that is n into d, right? So propose this relation, that is I and the wave number k, capital K of course, function of is a function of omega and x distance, this distance xd. Xd is nothing but nd, right? Yes. So actually we can keep this value. We can have the value of u naught from equation number 4 to equation number 3. Similarly, we can have for equation number 3, that is we can have v naught in terms of capital V is a function of kw. So see what we can have, this k, that is the wave number, actually is, that is 2 pi upon lambda. The lambda actually is the wavelength of the vibration wave, right? It may be sound wave, whatever. So this wave number, that is capital K, which is a function of omega, is nothing but 2 pi upon lambda. So actually if lambda is high, then wave number is low, right? Yes, this is the wave number. Further, this constant, we can have this mu times capital K W C D. Actually, mu is a constant, just since D is a constant, D is a distance between the two crystals or two meta atoms, right? Including the matrix. So actually, A is the size of the meta atom, and actually K is A plus the gap between the two meta atoms, right? Yes. So this is my relation. Then we can put the values from equation number from 4 to 3, and then I can write the expressions un, that is un is equal to capital U. So I am not writing, for example, this function. It's writing simple. So we have E and I. This is minus omega t plus this, say capital K into N into D. Excuse me. This is equation number 5. Similarly, I can have the same form for the motion of resonator. Excuse me. So Vn is equal to V naught e raised to power I minus omega t plus K and D. Question number 6. Right? Yes. Is that clear now? Now from onwards, you can see in my PPT. So these two equations should be remembered. That is, what Bloch has proposed and what wave number is. Just go. दूसरी PPT. So this is, now from here you can see the same thing again here. So what we have, we have this nth number of mass and spring, right? And actually whatever we have discussed is mentioned here. Now, so you can see this, the forces which you have seen, right? These forces and piezoresonator spring. We actually use Kp. Here it is written Kp effective. And we have these two, one equation is this, second equation is this. Yes. And then this is the solution which we have discussed, right? Solution for the displacement or motion of spring, main spring, mth spring, and the corresponding resonator. So basically what we have, whatever masses we have on the mainstream means the main structure, we also attach the resonators. So we attach say Mn resonator, say that is Mr. Similarly, we will be attaching say Mn minus 1, we will be having say Mr minus 1. So actually every mass of the main string, right, is supported with the resonator. It is because we want to diminish the low frequency wave or high wavelength wave. So this is the solution, right? Now, if you would see this, since we want to use here this un plus 1 and un minus 1, so we have to substitute the value of u here, right? So we know actually un, we know the expression for un, that is un actually is this. We can write the same expression for un plus 1, right? So actually un plus 1 will be what? Un plus 1 is equal to capital U e raised to power I n plus 1 k into d, so, and the minus omega t. Similarly, we will be having Vn is equal to capital V e raised to power I n minus 1 kd. Yes. So we can put this, and if you will determine this so-called un plus 1 and un minus 1 from here, then this actually is right. This will be the expressions, because this is what, this is the exponential term. So it would be what? It would be u into cos nk d minus omega t plus I sin nk d minus omega t, right? Similarly, we can write for n minus 1. If you will do this exercise, then I want to determine this expression, will be having this value, right? That is 2 times u cos kd e raised to power I n k d minus omega t. So we already know un, this is un. So if you know un this, then put the value in this equation number 1. Same thing we can do for Vn. Vn of course we know, right? Vn. Substitute the value from these equations in equation number 1, and if it is so, then we will get this expression, omega square into m. This is mn, right? So since actually all the masses are the same, right? Same masses, so put mn or m, does not matter. So omega square into m, capital U is equal to k, 2 cos kd minus 2, of course capital U, plus kp effective v minus u. Rearrange these equations and we have these expressions, right? This one arranged, we have these expressions. Yes? Yes. Now, Same thing we can do for equation number 2, that is in this equation of resonator, put the value of Vn and Un and write that is this expression. So we got equation number 4. Yes. Now, then the both equations 3 and 4 we can write in the matrix form. We can, even you don't want, you cannot just solve these all two equations simultaneously. So we have these two equations. Now for non-trivial solutions for this matrix equation, this must be 0, determinant of this matrix, right? So if you will assign this equal to 0, then you will be having this expression. This equation is known as dispersion relation. Why it is? Because that has relation between the frequency and the wave number, right? Now, so actually till now what we have done, we just considered resonator as a simple mechanical body, right? That is that resonator with having mass, nothing else. So actually if you have this resonator, then it will not do anything. I mean, it can not do anything, of course. You need to have, if you want to behave this as a resonator, then you need to have a higher mass, or else you can have some external energy, or you may be having some other source. The idea is we want to behave the mass Mr as a resonator or as a local resonator. And here we are going to do this with the help of piezoelectric metamaterial, right? So up to this step there is no problem, right? Everything is clear. Now coming to our main part, that is for piezoelectric, right? So basically now here I would like to yeah. So actually, as I told, no, this equation actually, this Q is equal, this is the piezoelectric equations. So as I already told that we have this no equations which you are aware of. Piezoelectric, we have this D, that is electric displacement or charge per unit area is equal to what we have, piezoelectric coefficient into strain plus permittivity matrix and the electric field, right? We have this. Actually, I want to write this equation in this form. So what I will do, I will integrate this d over small area, say. So this is E epsilon dA, B epsilon dA, right? This actually is known as a Q, right? Charge. And this, so we have, I mean electric field, right? So this is my electric field. And this is, this term say of course E this dA and this is B dA. We can write electric voltage upon this is B voltage upon T and this is my dA, right. So, this actually this term, this is voltage B upon T into area and voltage part should be separated. So, but actually this term is B upon T into dA is known as Cp, right. Actually Cp is integration over B dA upon T, right. Similarly here this is actually area, right. This part, that is this is area and we can have this into width into length or displacement. So, this actually displacement, say for example here BA and then this is Cp and this is say electric voltage and this part E, we can write this say width into the distance, that is relative distance of Bn minus Un plus Cp B. So, this actually is known as theta and this relative distance is known as so theta, right. And Q, just to make a difference, so we have this Q, this is my theta and this is the X and this is the Cp. Same type actually we can do, same type of of change we can do in our inverse piezoelectric equations. So, we have this equation, actually this equation. Now, we want to implement these equations for the local resonator and how it would be. बताना पड़ेगा. So, I hope this equation is clear, right. Similarly, we can do for these equations. So, actually Km is a short circuit mechanical stiffness and theta is electromechanical coupling coefficient, Cp is a capacitance. Now, electrical boundary conditions. So, what we have seen that piezoelectric material actually behaves as the capacitor, right. This is a piezoelectric material and we have now shunt network or shunt circuit. Let us we have only inductor, for example, right. This is my inductor. So, voltage across this and this, that is this B. So, of course, Z, right, that is impedance. So, we have this B is equal to IR, and actually I is current, and we can determine current by differentiating the charge, second equation of piezoelectric, so called direct piezoelectric effect. So, we can put here. So, this equation links electrical response to mechanical motion. Now, express everything in the frequency domain. So, since we are expressing everything in the frequency domain, this actually we already know that is relative displacement. So, since we have a displacement of main mass, so called Mn, and the Mr in the harmonic, therefore it will also be harmonic. So, therefore we can have this expression xe minus omega t. So, since this is my harmonic, then Q will also be harmonic, right? Since displacement charge depends on the relative displacement, so this also harmonic. And just to differentiate this, to take the current for this equation. So, differentiating this equation, we can have Q dot is equal to I omega, right? Q, yes, of course, QT, right? Then, but we have this voltage, that is this voltage. Put the value of Q dot in this here in equation number C. We have equation number D. Yes. So, yes, here equation number D, right? Now, we want to actually eliminate V voltage. So, from equation V, this equation, just put the value of V which we determine in terms of frequency and substitute here. So, we can put this value, and then we have this expression Q is equal to theta x minus I omega Cp Z Q. We can take Q common from this and this, and hence we have Q this term and is equal to theta x. Therefore, Q is equal to theta upon 1 plus I omega Cp Z omega x into E. So, we have this expression for the Q. Q means charge. So, we determine charge in terms of theta. Actually, this theta is coupling matrix. Actually, this theta includes D matrix or E matrix, piezoelectric coefficient matrix, right? And of course, there are some other quantities as well. So, since it includes the piezoelectric coupling matrix, so we can say coupling matrix. So, we have this equation E. Now, substitute back to eliminate B from force equation. So, we also want to eliminate this V. So, substitute the value of force in terms of omega. So, in terms of impedance. So, we have theta F is equal to Km x minus theta, and we have this P is equal to this. So, F is equal to Km x plus I omega theta Z into Q, right? This is my force. That is the converse piezoelectric effect equation. Substitute Q from E. So, we determined Q here, and now substitute here. Then we have F is equal to Km x plus I omega theta Z and this value of Q. then we can determine the value of F, right. So basically, if you would see the spring law, F is equal to Kx, right. So since this is actually is the equivalent to K, so therefore we can give a name to this is the K effective, Kp effective. That is the stiffness of piezoelectric element. Kp effective actually is the stiffness of resonator or piezoelectric material in our case. Then now as I mentioned that, but actually we are considering only the inductor, and capacitor of course is the piezoelectric patch as such. So we have this network. Of course, you can consider this here any other type of combination of RL, or you can have even one more capacitor, right. So actually it is now many combinations. So let us to have a simple way, we have only inductor in the shunt. So we have, so basically the inductive shunt means the electrodes of piezoelectric patch are connected to an inductor, sometimes with a small resistor as well. So we can also actually add some small resistance. So let us, we do not have here. So why inductor? Actually, of course, why I have written here most common case in making the piezoelectric metamaterial. It is because piezoelectric patches behave electrically like capacitors, right. An inductor plus capacitor naturally form LC resonator, right. So LC resonator actually you know, right, from your electrical engineering basic course. That is XL is equal to XC, right. So we have resonators interact strongly with waves, and once we have this, since we have resonator, we can create a resonance, and hence that particular frequency can be diminished. Frequency means particular waves, right. So basically when we say particular frequency means particular wave. See, when we have a system, the system will be having suppose vibrations. Actually vibrations may include many waves. See, but actually whatever we have seen, we see only one wave. But actually that is a combination of many waves because there are many frequencies. So to diminish the complete vibrations, we have to diminish all the waves or all the frequencies vibrations. And since we have higher frequency vibrations, we have lower frequency vibrations, so actually we have to deal for all frequency vibrations. And in the starting I told that the periodic structure can diminish the higher frequency waves, but it cannot diminish the low frequency waves, right. How it can, that we will see later. We are talking about at the moment for the low frequency waves, because low frequency waves actually are very very critical, particularly for very thin structures, where we cannot add external masses, because external mass actually makes the system heavy, and also it cannot be controlled. But we have this Yes. Now, so electrical impedance of an inductor, we know this. So we can write this in the frequency domain. The frequency domain inductor resistance can be written I omega L, right? XL, right? XL, L omega. So I think you know, right? This inductor actually stores the kinetic energy, right? It is just like the mass of the system, so called inertia force. Similarly, in the electrical circuit, the actual inductor behaves as an inertial element. So it stores the kinetic energy, right? Yes. So see, of course, are you already aware of? So omega omega is angular frequency, L is inductance. This impedance is purely imaginary, since we know I, right? It stores energy, no dissipations, and produce phase shift, right? So once we have this value of Z omega in terms of frequency domain or in terms of frequency, we can substitute this value here to determine the Kp. Kp effective is equal to this value Km plus this whole. Put the value of Z here. Again see, depends what shunt you are taking, and accordingly you will be having Z, right? The Z is the resultant impedance of the shunt. So we can put the value of Z here to determine the Kp effective, and hence Kp effective actually is this Km plus I omega Z square Z omega. Yes, actually I am putting now Z omega is equal to, in this expression you can put here, and if you would see this numerator, right, this one, actually it would be, since this is I, so it would be this one, and already I we have, right, and I is this I, so I square, so there will be minus sign. Then the denominator, this one plus I omega Cp Z, this is 1 minus omega square L, this is Cp, capacitance of the piezoelectric material, and the Kp effective is equal to overall, then after putting this all three values here, then we will have in this value Kp effective here. So Kp effective is determined, right? It should determine the stiffness of the piezoelectric material. Now we know in the electrical circuit resonance, that is XL is equal to XC, and in that case we will determine the omega E, that is resonance frequency. So omega is equal to 1 upon under root LCP. Yes. So see, this value 1 minus omega square LCP is equal to 1 minus omega square omega E. Basically, if you would see here 1 minus omega square LCP, we want to substitute the value of this, right? So to substitute this, we are just doing this one. So after substituting this value in terms of omega E, we have Kp effective is equal to Km 1 minus omega square upon omega E square. Now see, the stiffness of piezoelectric material actually is totally dependent on, can be controlled or can be tuned, right, with omega E. And we know omega E how it is. To change the value of L, and you have this omega E change, right? So means the stiffness of, the effective stiffness of piezoelectric actually is changing. See again, as such the stiffness of piezoelectric metal is constant. This is mechanical property. But during the operation, right, during the operations, because of the dynamic behavior, we have the variable Kp effective, right? We change the value of L and we change the value of Kp. So now see frequency regimes and their meanings. So determined only by the circuit, and this is, that is the value of L, independent of mechanical properties. So as such there is no mechanical property here, electrical, everything. Easily tunable by changing L. This makes the metamaterial programmable, right? So basically now we can play with this. So for low frequency regime, that is omega is equal to omega less than omega E. So in that case, Kp effective is equal to Km, right? See here, if it is very small than this, then it will be equal to this. So in that case, inductor behaves like short circuit, piezo behaves like ordinary elastic spring, and no metamaterial effect, right? In the resonance regime, this is, so K effective equal to 0. You see interesting now? So much interesting now. If we have resonance, then the effectiveness of piezoelectric metal is 0, right? So that is all about now the metamaterial concept. So what we have now, we have seen that when we have omega equal to omega E, then Kp effective is equal to 0. So electrical response absorbs mechanical energy, right? Electrical resonance absorbs mechanical energy. Piezo spring behaves very soft. Strong wave resonator interaction, and hence now this we have band gap opens. That is, there is no frequency stopping, frequency is passing. High frequency regime, when omega is equal to more than omega E, then Kp effective is equal to small. So negative effective stiffness, right, less than 0. So mechanical instability suppressed by the inertia, and you can see the stop bands, right? So finally what we have now, we can replace Kp, right, by Kp effective in our derivation part, that is in this expression. In fact, we have used Kp effective only here, right? When I started my discussion, I used Kp there, or Kr. So I can replace now Kr by Kp effective, right? So this Kp effective can replace in this, and then accordingly we can play. We want to increase Kp effective or decrease Kp effective, just playing with the help of L, so called inductor. So, this is all about the diminishing of waves or passing of waves, right, with the help of piezoelectric resonators.
So can we optimize this inductance?
Yes, we can optimize. Yeah, we can optimize. So actually, see again, if you will optimize, then you will be having one value. Though actually the optimization concept was good, no? But it is now obsolete. See, if you remember what we were doing in the optimizations, suppose one value is increasing or the value is decreasing, we actually want to have some compromise value, right? But actually nowadays we do not compromise. We want that one should actually both should decrease or both should increase or vice versa, right? So we want to design our structure in such a way that the desirable properties should behave according to our wish. It is not that we are compromising. So if you are compromising, then of course you can go for the optimizations. But if you don't want, then you should use the concept of metamaterial. Now see, in my discussions, if you would notice carefully, but actually what I did, here it is not there, I have used a plate, right, and actually I inserted or embedded the piezoelectric material. If the piezoelectric material actually are bonded on the surface, then it will not be metamaterial. Why it is so? Suppose I have patches, of course, and I have bonded on the surface, then actually it will not be metamaterial. Metamaterial will be only if you have embedded inside. Why it is so? It is because if you have bonded, then actually it is not composite material, right? Composite will be only if you have embedded, you have in the phase. As per the definition of the composite materials, we have two macroscopic phases. So actually it must be embedded, right? So that concept actually is new, and now people are working on this. So we have actually discussed that, or we can play with the lower frequency vibrations. Now what about the higher frequency vibrations? As I promised, as I told earlier, that we can actually diminish, not we can, the concept of meta atom actually can diminish vibrations of high frequency. So how it is, that we will discuss.